Today we are going to look at 1.5 in the workbook, so please get your workbook out so that we can look at section 1.5 in there. I guess before I dive into that, are there any questions on the XYZ homework problems that are due this Friday? If you've begun working on those and you run into any issues, this would be the right time to ask.
I honestly just barely started because I got busy with other work.
Okay. Okay, no questions. So we can start into the 1.5 inverse functions workbook section. So we talked about the Fahrenheit to Celsius conversion in one of the earlier sections. This is an example of a function that we can find the inverse of, because we can essentially, we had an equation for converting from Celsius to Fahrenheit. What we can do is we can kind of invert that to in order to find a formula for Celsius if we know what the Fahrenheit measurement is. So how would we do that? The temperature in degrees Fahrenheit represents a function of the temperature in degrees Celsius given by this formula here. Find the temperature in degrees Celsius when the temperature degrees Fahrenheit is 365. So if they're telling us the temperature in degrees Fahrenheit, that's going to be our F. So F is equal to 365. Which means we're going to replace F with 365, and then we're asked to find the Celsius equivalent of that. So we would set this up as 365 equals 9 over 5 times C plus 32. Right, once we've set it up this way, it is as straightforward as just solving for C. So let's go through the steps of doing that. The first thing we would want to get rid of is the 32. So we're going to subtract 32 from both sides. Get 333 equals 9 over 5C. And then can anyone tell me how we're going to get rid of this 9 over 5 so that we can get C by itself?
Multiply each side by 5/9.
Good. If you want to get rid of a fraction, that's multiplication. You multiply by its reciprocal, 5 over 9, in this case, on both sides. So 333 multiplied by 5/9 is going to be... what is that going to be? 455 divided by 3, which is 185. So the answer is going to be 185 degrees Celsius is the equivalent of 365 degrees Fahrenheit. Okay, now we could keep doing this, right? If we know the Fahrenheit measurement of a temperature, we could always just set it equal to this formula like we did, and then do these steps to get to find C. But we don't want to keep doing the same minus 32 and then the times 5/9, which you would have to do every time to do this. So instead, what we can do is we can.
Why is there fractions? What does that even mean? Like those fractions? Are we dividing?
Where?
I see those 9/5s. What are those supposed to be?
This?
Yeah, those like.
That's multiplication.
Multiplication?
Yes. So when I put parentheses like this and I put a 5/9 next to it, that means we're multiplying by 5/9.
So how am I multiplying it by 5/9? Like, am I crossing?
Well, we're multiplying by 5/9 specifically because we had a 9/5 in there, and we wanted to get rid of it. So we're multiplying 9/5 and 5/9 together, which, yes, not cross multiplying, but the 9s cancel and the 5s cancel, so that cancels out completely. And then on the other side, we're doing 333 times the fraction 5/9 on this side.
Wait, so we're multiplying. Wait, what are we multiplying? Like on the left side again?
We're multiplying by 5/9.
How do we do that?
How do we? You need to review fraction multiplication. We don't have time to go back and review that right now.
All right.
Okay, like I said, we could keep doing that every time we know the Fahrenheit measurement, or we could solve for C in terms of F in order to have a formula for it. So we only do this operation once, and then we'll have a formula for how to get from Fahrenheit to Celsius. So how we're going to do that is we're going to start with this function here, the F equals 9/5 C plus 32. And instead of having a function F, a function of C, we want to have C by itself and then have some stuff that has to do with F on the other side, right? We want to have C be a function of F. That's what it's asking for here. So we need to isolate the C in this situation to invert this so that it's C in terms of F. How we're going to do that is essentially what we did on the last problem. We're going to, we want to get this C by itself, so we need to get rid of the 9/5 and the 32, or we need to move them to the other side. First thing would be to subtract the 32, just like we did last time, but now there's no numbers to deal with. We don't know what F is, so instead of subtracting 32 from F and getting a number, we're just going to write F minus 32 here. And the next thing we're going to do is we want to get rid of the 9/5, just like last time. How we get rid of that is we multiply by its reciprocal. So again, we multiply both sides by 5/9. On this side, things cancel nicely like we wanted. And then on the other side, we'll just leave things as is. So now that we've isolated C, it's by itself on one side of our equation. That is going to be our function. This left side is going to be the function g of f that the question was asking for. So we've just taken an equation that is f equals some function of c, and we've converted it, isolated the c, so that now we have a function c, that is in terms of f, right? So we've kind of reversed the roles of the variables here, the inputs and the outputs. So in this function here that you're seeing, f would be my input and c would be my output, right? In the original function, we were inputting a degree Celsius measurement and outputting Fahrenheit. Now we flipped that. Fahrenheit are the inputs, Celsius are the outputs. So this process of flipping the function around so that the inputs and outputs are flipped is called finding the inverse of a function. Sorry, I guess it's right here. These are called inverses of each other. And then if a function has an inverse, then we call that function invertible. That's just definitions at the bottom here.
So that's the answer?
Yes.
So is the answer like yes, it's a function or something?
No, the answer is the thing in the box.
Oh, okay. Just, we don't have to write anything else?
The question was asking for that, so we gave that as the answer.
Okay.
Okay, moving on. Inverse functions are defined as follows. If we have a function y equals f of x, its inverse is written with this notation, f inverse, that little exponent of -1. We read that as inverse. So this is x equals f inverse of y. Okay, let's see if we can look at this example here. Example says the number of cubic yards of dirt. So we've talked about cubic yards of dirt before. This is relating back to a previous example. Needed to cover a garden with area A. So area is A. It's in square feet. Is given by the function D equals G of A. Explain in words the meaning of each of the following statements. So if G of 2500 is 25, let's highlight this in different colors, I guess. In this function here, real quick, the D equals G of A, which one is my input and which one is my output? In this, is D the input or A the input?
D is the input?
Which one?
D.
No, A is going to be our inputs here. And D is going to be the output. Right, because we plug in inputs into a function, the function being G here. We input the area of the garden, and then the output is the cubic yards of dirt that we need for that garden. Right, so here in this expression, G of 2500 equals 25, which one is the input and which one is the output? Is the 2500 the input or the 25 the input?
25 is the input.
Why do you say that?
Because Oh wait, no, I got mixed up. 25 is the output.
How do you know that?
Because it represents the D, because G houses the input, so 2500 will be the input.
Good. And 25 is the output, right?
Yeah.
Good. So now we can talk about, you said 25 houses the input, which is the A, right? So this is input, comma A, output, comma D. So we can write a sentence about what this expression means in terms of like yards, cubic yards of dirt and area in square feet of the garden, right? So the sentence here that we want to write about how many cubic yards and how big the area is would be that this expression represents an area, a garden with area 2,500 square feet needs 25 cubic yards of dirt to cover it. Right, that's what that G of 2,500 equals 25 represents.
What is that Y that needs 25? The 25 does that say?
This is cubic yards, so yards cubed.
Okay.
What part B is showing is that, remember this is G inverse, right? So this is the inverse of this function. So the inputs and outputs are switched here from before. So in this case here, in the second part of the example, this 25 that's in the parenthesis is the input for the inverse function, which used to be the output for the regular function. So this is actually going to be D, and this is going to be A. So nothing really changed from the first one. The 2,500 is still the A, and the 25 is still the D. Just the notation kind of switched. While G was computing, while G was taking an input of the area of the garden and outputting the cubic yards of dirt, G inverse will be doing that operation the other way. It will take input the the cubic yards of dirt, and then it will output the area of the garden that you can cover with that dirt. Right. So the first one was starting with the area of the garden and telling you how much dirt you need. This one is going to take how much dirt you have and tell you how big of an area you can cover with that dirt. So the sentence here is going to be kind of written backwards. So 25 cubic yards of dirt will cover a garden with area of 2,500 square feet. So inverting the function would mean the meaning of the function is inverted. The sentence that you form with the function is inverted. The inputs and outputs are switched. Okay. Let's do this example. I'll do both parts with you as well, or we'll do them together. We'll discuss these as we go. So using a graph, we have a relationship between x and g of x, which is the original function here, given by this blue curve, right? So if I told you x is equal to 5, then we would know that we would go up to this point here. This would be 5 comma 3, right? A point on the blue curve. That means g of 5 is equal to 3. Right? We plug in the x, we get the y value out from the blue curve. So part A says g of 3, which means we go to the graph, we look at x equals 3. And we go up to the graph and we see that the y value is 1. So g of 3 will be equal to 1. Right? That's from the graph because there's a point at 3 comma 1. What about g inverse of 3? How are we going to deal with that? Remember, inverse functions work the other way, right? Inputs and outputs are switched. So the number we're plugging in here.
The 5 from.
I was just giving an example.
Oh.
Here. I just did like one more example. If we were to do g of 5, it would be 3. I guess we don't really need that. But when we're doing g inverse of 3, remember the inputs that are going into the inverse function are y values. So we look at the y-axis, we go up to 3, and then we go over to the graph, and we see what its x value is. All right, so we do the operation backwards if we're doing an inverse function operation. So g inverse of 3 would be what?
5.
Good. Inverse is essentially you input a y value, you get an x value out from the graph. Okay, moving on to the next page. Example gives us a function that is an invertible function. It tells us it's invertible. Determine the inverse function by following the steps listed below. Okay, let's go through these steps. So these are the steps for how to find an inverse of a function. So this example here is going to be important to look back on when the question asks you to find the inverse of a function. These are the steps that you will follow. Okay, the steps are written out for you, so it should be pretty self-explanatory. First thing we're going to do is substitute f of x with y. So we start with our original function here, and we're going to replace this f of x with a y instead. So we, instead of writing f of x equals blah, 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 we're going to write y equals 2 over x minus 3 plus 4. All right, first step is to just rewrite it in terms of x's and y's. And then step 2 says to solve for x in terms of y. What that means is right now the function is solved for y because the y is isolated. If it says solve for x, we want to isolate this x. Okay, so we're going to start with y equals 2 over x minus 3 plus 4, and we're going to do algebra operations to both sides until we have this x isolated on one side by itself. That's what isolated means. So I'm going to give you 3-4 minutes to see if you can get this x by itself. Go ahead and try it on your own, and then I'll go over the correct steps so we can all check our work. Okay, so I'm going to give you 3 minutes to get this x by itself. Okay, hopefully you made some progress towards getting x by itself. Can someone tell me the first step we want to take here to getting that x by itself?
Subtract 4 from each side.
Good. We'll subtract 4 from each side. So we'll end up with y minus 4 equals 2 over x minus 3. Okay, that seems like the easy step to do. Next step may not be so easy. Did anyone come up with something we can do next to ratify the situation?
Add 3 to both sides.
Good idea, except the minus 3 is kind of locked in this denominator here. I can't just like add 3 to this denominator, right? Because that's not necessarily just adding 3 to that whole side. If I wanted to add 3 to the whole side, it would look something like this, right? We would add 3 to the whole fraction. Unless that's what you wanted to do. Which doesn't really get rid of the minus 3. So how are we going to break that fraction apart, kind of?
Multiply each side by x minus 3.
Yeah, that's not a bad idea. So let's do that. The issue with this is that we're trying to get x by itself, but x is stuck in a denominator, right? So we really don't want it to be in a denominator. So good job, Brian. The best way to get rid of that is to just multiply both sides by x minus 3 in order to kind of lift that x expression out of the denominator.
What about 3 minus x?
We want the x minus 3's to cancel, so we would want to multiply by x minus 3. 3 minus x is not the same thing as x minus 3, so I wouldn't do that.
So, but with fractions, it's the other way around. You just flip them upside down.
If you're trying to get rid of the whole fraction, yes, but we're just trying to get this denominator out of here. Because we don't want x's to be in the denominator anymore. So this allows us to kind of, on the other side, you see how it's lifted out of a denominator, right? It's no longer in the bottom of a fraction. So while on the right side, these are going to cancel. On the left side, we're going to end up with x minus 3 times y minus 4, and we'll just leave that like that for now, equal to 2. And we see that there are no more fractions. And most importantly, we see that x is no longer in the denominator of a fraction, which is good to see. Now, we could multiply this out, right? When you see like two binomials multiply together, we have a way of multiplying that out. We don't really want to do that, because if we do that, we're distributing this x into the second parenthesis here, and we're increasing the number of x's that are in our expression. What we could do instead is we could keep this here and just get rid of this y minus 4. How would we get rid of the y minus 4?
Multiply.
By what?
Y minus 4.
That would just square it. I want to get rid of it. I want it to cancel. So we're...
Add 4? Yeah, add 4.
Adding 4, I think it seems like you're trying to just get rid of the 4. I'm trying to get rid of this whole parenthesis here, the y minus 4.
Divide by 1 minus 4.
Good. Let's try that. If we divide by y minus 4, the whole fraction, or the whole parenthesis, will move to the other side as a fraction. So here the y minus 4's are going to cancel on the left. So we're going to end up with x minus 3 equals 2 divided by y minus 4. All right, so just like how we multiplied by x minus 3 to move the x minus 3 to the other side, we can just divide the y minus 4 to the right side. Right? We can divide both sides by y minus 4, and it ends up in the denominator on the other side. And finally, we want to get rid of this minus 3. So how do we get rid of that minus 3?
Add 3 to both sides.
Add 3 to both sides. Good. So we'll end up with x equals 2 over y minus 4 plus 3. and that's step 2. Step 2 is where most of the work is going to happen for this process of finding the inverse function. First step was very straightforward. We just replaced the f of x with y. Second step is where we do most of the work of kind of switching the roles of the inputs and the outputs, right? We used to have a function where we would plug in a number for x and we would get a number for y out. Now we've turned this into a function where we're more likely to plug in a number for y and do this operation and then get an output of x, right? So we've done that kind of switching of roles of the inputs and the outputs here by taking the original function and solving for x. So we solve for x, that's going to be our expression in terms of y. Step 3 says interchange all x and y values. What that means is literally start with start with the result from step 2 and take your x and y, and we're going to swap their places. We're going to interchange all of the x's and y's, so we're going to switch those roles
Oh, mister, I'm bleeding through my nose.
right now.
I'm
Okay.
gonna- It's
You
called-
don't have to tell me,
Oh.
just go. We're going to interchange the x and the y because we're essentially inverting here. We're swapping the inputs and the outputs. So when we do that, we just swap their places physically. So y equals 2 over x minus 4 plus 3. So I guess we should make a note of this. This is turning into this by swapping the x and the y. Right, so I just swap the x and the y to get your step 3, which again is a pretty simple step. So step 2 is the only step that we had to do a bunch of work in. Step 3 is very straightforward. You just switch the x and the y and you get a function here. Now that we've actually swapped x's and y's, this y here that we have in step 3 is not the same y that we started with. Okay, this interchanging of x and y values creates y equals f inverse of x. So this y here is now represented by f inverse, right? That physical action of swapping them means that this y is actually f inverse. So now we're going to replace this y with f inverse, just kind of undoing what we did on the first step here. We replaced f of x with y, and now that we've swapped the x and the y, this new y is f inverse. So we're going to rewrite this with the f inverse notation. And we're going to box that because that is going to be our inverse function. So let me zoom out a little bit so we can see the whole thing step by step. Any questions on the steps?
Yeah, sorry, I got a really different answer, and I'm kind of confused because I kind of use a different method, and
Okay, what did you do?
because I foil and then I factor out the x from
Okay, let me
the x minus 3.
Yeah, so when you FOIL, you get xy minus 4x minus 3y plus 12, right? Equals 2.
Yeah.
What is your answer? Sorry, tell me what your answer is.
Because my answer was y equals negative 10 plus 3x divided by x plus 4.
That
Or x minus 4.
x minus 4. That is the same thing, I think. If I were to take this 3 and this fraction and get common denominators, so like, you guys don't need to write this down, but let's just confirm that that is the same answer here. If I take the 2 over x minus 4 plus 3 and I change this to x minus 4, we get common denominator here. Distribute this 3 and then combine things. 2 plus 3x minus 12 over x minus 4. Right? The 2 and the negative 12 will give me the negative 10 that you have. And we have the plus 3x over x minus 4. So you're fine.
Okay.
It just looks different. I would advise against the foiling here and then refactoring out, just because this gets you to a nice answer a little bit quicker.
All right, thank you.
So whatever you got, this answer is mathematically the same thing as that. So don't worry about it. You can write your answer however you want. Okay. Any other questions on the steps?
Which was the answer for number 2?
This here.
Do I swap out the x and y?
On step 3, yes.
Okay.
So we get x isolated in step 2. That's the whole point. And then we swap the x and the y for step 3. And then all we do is just replace the new y with f inverse of x for step 4. Okay. So essentially step 1 and step 3 and step 4 are very like short steps where you just switch the f of x to y, where you swap the x and the y physically, or you replace the y at the end with f inverse. Most of the work goes into step 2.
So number 3, you just interchange. That's
Yeah.
it? Okay.
Okay, let me see what else we have here. You guys can do that example. I believe in you. Let me talk about what's in this box here, and then I think you guys can do... I'll get you started on this example, but you guys can do that one as well. This box is talking about how to verify or how to check if two functions are inverses. So this is saying that f and g are inverse functions if you can show that these two conditions are satisfied. Now these two conditions are saying that if I take one function and I plug it into the other one, so if I do f of g of x, it should all simplify down to just x. Right? And then the second condition is kind of the reverse condition. If I take the function f and I plug that into g, then again everything should simplify down to just x. So if you can show both function compositions, f composed with g and g composed with f, and they both simplify down to x, then you can conclude that f and g are inverse functions. So you'll be doing that with this example here down here, where you need to evaluate, or not even evaluate, let's say simplify f of g of x, which we learned how to do last week, I think, or Monday. We did function composition. So we should know how to do f of g of x and g of f of x and show and check if they simplify to x. So we're going to do function composition. You're going to do f of g of x and see if that simplifies to x. And then if it does, you'll do g of f of x and simplify that one and see if that one also simplifies to just x. Okay, so that's kind of the what you're going to do to determine if they're inverses. And if they do both simplify to x, then it's a confirmation that this g and f are inverse functions. So if they do simplify to x, then the answer is yes. If they don't simplify to x, or if one of them doesn't simplify, you can stop there and say no. Okay, you don't have to check the other one. If you check the first one and it doesn't give you x, or if there's no way to like simplify things all the way down to x, then you can stop and say no. Okay, so you guys will be doing,
Wait.
yeah.
So is this supposed to be like a word question? Like you have to like write down a sentence?
The answer is going to be yes or no in the end. But the work is going to be to compose these functions. So you're going to have to take this function. Remember how we compose functions? We're going to take this function and we're going to plug it into the other function. And then after you do that, you simplify it and you see if it simplifies completely down to just x. And then you're going to take this function, f, and plug it into g of x and see if that simplifies all the way down to x. So no, it's not a word problem. I don't exactly know what you're asking, but it's not a word problem. You have to do you have to actually simplify these function compositions.
Okay.
Domain and range. Let me just put a note here at the top of the page here. We'll say when inverting a function, the domain and range switch. Right, we see that in that step 3 where we interchange the x and the y in the process. That's going to switch all of our domain values with all of the range values. Right, so if you have the domain of the original function, if you know the domain of the original function, that'll end up being the range of the inverse function, and vice versa. If you know the range of the original function, that'll end up being the domain of the inverse function. So you should be able to answer some questions about domain and range here. Let's move on to, you guys can do that one as well. It's just using the previous example, using this set of points to do the graph. You guys can graph points on a graph. I believe in you. Restrict the domain of a function to make it one-to-one. Do you guys remember what one-to-one means?
No.
Anyone remember what one-to-one means?
It's when the outputs have, like, each of the outputs have one input.
And
each of the inputs have one output.
good. In terms of graphs, do you remember the tests for one-to-one?
The first, it's the vertical line test to see if it's a function, and then the horizontal line test
To check if it's one-to-one. Good, perfect.
Yeah.
So looking at this graph here, in this example, does it pass the vertical line test? If I draw vertical lines, do they always hit at exactly one spot?
Yes.
Yes. So this is a function. Does it pass the horizontal line test?
No.
No, because if I draw a horizontal line out here, we hit 2 spots. Perfect. So this is not one-to-one to begin with, right? What this is talking about is we can restrict the domain of a function in order to make it one-to-one, right? We don't have to change the actual formula. So this is a quadratic with the formula y equals x squared, right? We recognize that as one of our one of our parent functions. What we can do is we know that x squared, the parabola, is not one-to-one. What we can do is we can restrict the domain. So if we only have like this side of the parabola, and we say let's not look at the other side of the parabola, then it passes the horizontal line test, right? So you see a picture of it down here where we just have the right half of the parabola, and we've defined the domain to be 0 to infinity instead of all the way from negative infinity to infinity. So if we restrict the domain to just be from 0 to infinity, now if I draw horizontal lines, it always touches at one point, which means this is now one-to-one. And because it's one-to-one because we restricted the domain. The reason why we need a one-to-one function, why would we do this, is the question. The reason why we would need to do this is because we can't invert functions unless they are one-to-one. So let's make a note of that. We need one-to-one functions to invert. We can't invert non-one-to-one functions. So this is kind of like a loophole to get around that. Even though x squared is not a one-to-one function, we can turn it into a one-to-one function by just restricting the domain, and then that'll allow us to find an inverse for it. Now the inverse that we find will have to do with this restricted domain as well. So we can't lose that domain restriction when we get to the inverse. But it allows us to find the inverse in the first place. So we got to know how to restrict domain to make functions one-to-one. You guys can do this example. Just follow the steps that we did on that example that we did to find the inverse, where you change the f of x to a y, you solve for x, you swap the position of the x and the y, and then you write it as f inverse. You can do all of that with this function on this example. Okay, so we'll say follow the 4 steps as like a hint for that one.